Good evening, everyone, and welcome to Airbus Defence and Space. I'm Laszlo Sic, the host of the evening, and on behalf of the Royal Aeronautical Society, Stevenage branch, we are very proud to host the very first public lecture of our public lecture series of 2026. Um, I don't want to talk too much, but before I give the word over to our speaker, Robert Baldwin, I would like to mention just a couple of housekeeping rules. So we're not planning on any fire alarm tests, but if the fire alarm does go off, could everyone please just follow us towards the entrance where we came in? Otherwise, that's all pretty much, isn't it? Yes, so I'm very proud to introduce our tonight's speaker, Robert Baldwin, who is an Arthur C. Clarke Lifetime Achievement Award winner. He received his achievement in 2024 for his outstanding work in satellite propulsion design. Robert has spent 20 years in telecommunicational satellite design. He also spent 25 years in the area of satellite science. So with over 45 years, well, actually coming to 45 years of experience in satellite propulsion technology and having managed several engineering teams, I am welcoming him to take the microphone. And can we give a warm applause? Thank you.
Yeah, so can you hear me all right? Yeah, good. Thank you for coming. Yeah, so I come from the North District of Bristol. So if you're aware of Filton and Patchway, I went to school in Patchway. So my father was he left school at 14 and became a coppersmith at the BAC in Filton. So I think he left school during the war and went straight into aircraft engine manufacture. So he was a coppersmith, and then I was aware that he was working in jig and tool at BAC. By the time I could sort of get into the factory with him and be shown around, he was doing PERT planning for things like Concorde. And so I've been brought up with aerospace right from the youngest age. And it's not a surprise that I ended up in aerospace myself. I did maths and physics and chemistry at A level, and I was fortunate enough to get chosen to go on to a scheme in industry. So in my sixth form, I was given afternoons, one afternoon a week, to go into Rolls-Royce and BAC to do a project. So the project I did as a sixth former was to design a probe. So sorry, that was later on. The school project I did was the application of lasers in aerospace industry, where we were observing they were using a 500-watt laser to cut metal out and to also cut out fabrics. So that was an industrial project which I did as a sixth former, which is like the thing called an EPQ these days. So after doing my maths, physics and chemistry, I went to Oxford, where I did a general engineering degree and specialized in, let's say, thermodynamics and fluid dynamics. And I did a third-year project, which was sponsored by Rolls-Royce, and that was where we come to this probe. So it was a very miniature probe doing total pressure, static pressure, and flow angle, and it was used to monitor the flow coming out of the turbine blades for Rolls-Royce. So that was a great third-year project to do. So not surprisingly, I kind of ended up here. So I came here in 1981. So in a couple of weeks' time, I reach 45 years. So I think this is a sort of anniversary lecture by me. So yeah, what we see there is the sort of place where our science projects operate. So we've sent spacecraft to many planets, and hopefully in the news this year we will hear about Bepi Colombo, a spacecraft we designed 3 propulsion systems for. Bepi Colombo is going to arrive at Mercury this year. Okay, so what you see on this picture is where we operate. So we send up space telescopes, space probes, and all sorts of science projects into space. My own career was from 1981 for 10 years. I was on the Olympus telecommunications technology demonstrator satellite. So that was the first bipropellant system done in the UK. And that was launched in about 1991. And then I did another 10 years on telecommunications satellites, where I was working on our Stevenage Eurostar spacecraft product. After that, I changed over to being operating on the science spacecraft. So lots of interesting projects. I've been team leader, so on many projects I was the boss of the architect who was designing the spacecraft. So yes, I've just run through the sort of propulsion systems. So and against the timeline of the earliest ones I can remember. So I remember being employed here when SOHO was just a future dream. SOHO is a science mission studying the sun. XMM is a X-ray telescope. So X-ray multi-mirror is it focuses X-rays by having lots of shallow angle cones mirror the embedded layers of conical mirror inside. So the X-rays will only deflect a little bit to come to the focus. So X-ray telescopes are always quite long ones. Okay, so SOHO and XMM will be using propulsion, hydrazine propulsion systems. Why do spacecraft have propulsion systems? So the answer is 1, to get them in the right place, and 2, to get them pointing in the right direction. So we have to point in the right direction if we have let's say a telescope or a telecommunications payload, which has to point at a certain country or continent. So in the right place, pointing in the right direction. And so the whole spacecraft system all works together with thermal control, with the sun acting on certain intended faces, and the payload pointing, and the solar arrays getting the power in. So just by way of interest, one of the jobs I was on was the Olympus technology demonstration satellite, which after about 3 years of operation, it span out of control. So the spacecraft operator didn't follow a approved procedure, and they lost control of the spacecraft. So one of the interesting jobs I did was to be on the team which brought a spinning and lost spacecraft back to life. So it was spinning out of control for about 8 months, and we gradually gathered data, and we got to the point where there was, let's say, sunrise. The sun was rising on these solar panels, which were kind of pointing in roughly good direction, as the months went on, the sun rose, so we got more and more power on them. And then we went through a process of charging the batteries. The propellants on the spacecraft had gone to, let's say, minus 65 degrees C. So one of the propellants was absolutely totally frozen solid, and the other propellant was roughly turning, just about turning at minus 65 C. So we eventually got enough charge in the batteries to be able to heat the propellant tanks for a month to thaw them out and turn them from solid propellant back to liquid like they should be. And that spacecraft came back to life. So that was interesting. And in fact, that also happened to the spacecraft called SOHO. That suffered a similar fate halfway through its life. SOHO is still going today. So yeah, the propulsion system is there to get it in the right place, pointing in the right direction. So it's got an attitude control function. So pitch, roll, and yaw. Often we have thrusters which are in all those three axes, and combined with other features which the spacecraft system has, such as wheels, so reaction wheels. If you spin a reaction wheel in one direction, the spacecraft rotates slowly in the opposite direction, and momentum wheels, which are like a gyroscopic equivalent of reaction wheels. All of those attitude control features on the spacecraft are combined with the propulsion system, which might do attitude control directly, or it might be used to, let's say, despin a wheel. So if you have an attitude disturbance which is always in one sense, then the wheel will spin up and spin up and spin up, and eventually a thruster will be used to fire a torque in the opposite direction so that the wheel is despun. Okay, so we have there a solar mission, an X-ray mission. Cluster 2 is a combination of 4 spacecraft studying the dynamics of the Earth's magnetic field, so Sun-Earth interaction with the solar wind affecting the magnetic field of the Earth. So that cluster spacecraft has been studying that. And then we have Mars Express. So we sent a spacecraft to Mars, and it did quite a few years and then ran out of propellant. That's bound to happen in the end. So I'm happy to take any questions directly. So I personally was, as it were, the time the boss of the propulsion architect for Mars Express, and then I did some work on Rosetta. So Rosetta was a spacecraft which was designed to orbit a comet, and the spacecraft had to go way out into the solar system in order to come back in unison with a comet. So the actual mission was 10 years to get to the science phase of Rosetta, where it orbited a comet, and it deployed a lander called Philae, and Philae was a partial success in that it landed and took its science data for a few days. And I remember when we had the televised event, so the European Space Operations Centre was beaming its operations during that time, and when Philae landed on the comet, the cheer was like a FA Cup final goal had been scored. It was fantastic. So yeah, I personally worked on Rosetta, and so yeah, I've shown you some some spacecraft so far which are monopropellant hydrazine propulsion systems, and Mars Express and Rosetta are using bipropellant, which is about 50% better performance. So we have a term in propulsion world which is specific impulse. So the performance is measured in how much impulse do you get per kilogram of propellant. So specific means per kilogram, and impulse is force times time. So the number for monopropellant systems is about 230, and the unit is seconds. And for bipropellant, it's somewhere in the region of 290 seconds. So yeah, Rosetta was a bipropellant spacecraft, and then we managed to sell to the European Space Agency a repeat of the Mars Express satellite. So a identical propulsion system was delivered in Venus Express, and Venus Express did a many years of science around Venus. Okay, so that was another bipropellant spacecraft. And for the when you orbit a planet, then there's a trajectory, you get put on a trajectory by the launch vehicle, and then when you get close to the planet, you have to perform a long thruster maneuver, which might be an hour of 400 newtons, to take you from a trajectory which is going to fly past the planet to slow you down, so then you're in a circular orbit around the planet. So all of that is we do the calcs for the propellant budget and everything for those. So I'm also interested in astronomy myself, so I know all about Herschel. So Herschel was I think it was a microwave science telescope, which Herschel and Planck were two similar spacecraft, and they had hydrazine propulsion systems, and they are placed in an Earth orbit. And so Herschel Planck, I was lucky enough to see one of those spacecraft in the clean room in Bremen. So you can see there the timeline getting to 2009 launch date. I was also working on Gaia, and Gaia was a space telescope performing astrometry. So it was taking all the parameters you want to gather about stars. So it studied 1 million or 1 billion stars in the local Milky Way to establish a sort of map of where all the stars are over time, because it would generate star locations every it would download the whole population of stars every sort of 18 months into the science community, so they could actually track the motion of stars in the Milky Way galaxy. And Gaia is a bipropellant system and a cold gas system. So the direct attitude control of a very, very low gas release out of a very small thruster is a fine way of doing attitude control. So Gaia had 10 Newton biprop thrusters for its orbital maneuvers, station keeping, but for the science, it had very delicate cold gas thrusters, which are micronewton level, I think. And we delivered the propulsion systems for those. Cheops is a hydrazine propulsion system in a planet hunting satellite done by Airbus. Sentinel 5P is a satellite which is purpose is to detect sorts of gases in the Earth's atmosphere, so it is able to, as it were, police the who in on the planet are doing pollution with industry. So it's measuring all sorts of chemical species in the atmosphere. And say I worked on a bit on Sentinel 5P and Solar Orbiter. So Solar Orbiter is currently, it was launched in 2020 during COVID, and it is performing observation of the sun. So it's in a elliptical orbit which goes close to the sun every 195 days. So it looks, its science phase is looking closely at the sun, and then it comes out in an elliptical orbit and back, and every 3 times that it comes back to this location, it is actually going around Venus. So it uses Venus to do a gravitational assist maneuver to change its inclination. So when it did its first orbit, it was in the plane of the planets, and with each visit close to Venus, it is going at an inclination, so it's moving to an orbit which is more looking at the poles of the sun. So that's gathering loads of interesting solar physics data. BepiColombo, I've already mentioned, is a mission to Mercury, and I think it was launched in about 2018. So a lot of these missions, I was lucky enough to go to the European Space Operations Centre and be there when they do critical maneuvers, such as the first propulsion activities after launch. And my colleagues in propulsion are being sent there this summer to witness and support, technically the technical specialists on the separation of BepiColombo. So BepiColombo has been using predominantly electric propulsion on its way to Mercury. So the electric propulsion is xenon gridded ion technology. And where I gave you numbers of 230 seconds for hydrazine, 290 seconds for bipropellant, the specific impulse of the electric propulsion system on BepiColombo is around 1400, so like four or 5 times as much. Okay, so I'll come on to that later. So BepiColombo is an engineering feat just to get it to Mercury orbit. Hopefully will happen this summer. It's taken a year longer than expected because of degradation of the electric of the power system. And then I do mention James Webb Space Telescope here because this site was involved in industrializing one of the payloads on JWST, and Airbus as a whole also delivered another microwave experiment to JWST from Holland. So there's a little bit about SOHO, and it mentions that it went into no, it doesn't. Okay, so yeah, what we can see there is the solar wind streaming away from the sun and a comet in that field of view. Okay, so solar heliospheric observatory. Does anybody have a burning question they want to ask? Yeah.
I was kind of wondering, JWST, what kind of weird with a weird shape.
Yeah, well, let's say astronomy missions have trended from optical to the other to microwave sort of wavelengths, which means that the instrument, the telescope for microwaves, has to be tooled. Okay, so it's got a science side with a telescope and a spacecraft platform side and a great big heat shield. And Gaia has a great big heat shield on it as well. Okay. Any other questions? Yeah.
Questions? Pass it around.
Yeah.
Grab it.
If you want to stop me and ask a question, feel free.
I assume that's recorded.
Sorry. Can you take the mic?
Such a stupid question. If we go back to the previous. I think that's the comment.
Yeah.
Yeah, and then what's this bit here then?
Well, the solar wind is all that stuff coming out in all directions.
Yeah, it's just it's quite different there, and I just wondered if there was a reason why it's just the way it's showing.
Yeah, it's just variation.
Okay, I was just
Yeah.
interested. Thank you.
Okay. Yeah, so another success coming out of Airbus is the LISA Pathfinder. So LISA is a gravitational wave observatory. So LISA, Laser Interferometer Space Antenna, is currently being designed, but the LISA Pathfinder spacecraft we delivered was in order to demonstrate that the technology required for the LISA complete mission was achievable. So we delivered one spacecraft, and that one spacecraft was used to demonstrate the ability to measure minute motions in space. So that has a technology package which releases a mass inside a cage, and the spacecraft tries to keep the mass right in the middle of its, as it were, cage. So it uses very, very fine cold gas thrusters to maintain the mass in the middle. So the mass detects local gravitational effects, and the spacecraft is aligned with that motion, the minutest of motions. So anyway, the LISA Pathfinder demonstrated that it would work, and now unfortunately it's being done by a competitor, but the LISA mission will fly 3 of them and be thousands times more sensitive than the ground-based LIGO. Okay, and yeah, it'll be transformative in terms of gravitational observation. Okay, yeah, so James Webb is using near spec instrument, and that near spec was from Airbus in, I think, Holland, and then the UK delivered the MIRI instrument, and Airbus here was sort of industrializing it. So there we see the Gaia spacecraft, which has its large sort of heat shield deployed, and on board it's got 2 telescopes. So the 2 telescopes, the spacecraft is rotating something like once every 6 minutes or something, and it is scanning the sky, taking the position of the stars as it goes. And this spacecraft uses bipropellant for the big propulsive requirements, and very, very low thrust cold gas for the very delicate attitude control. and there's a picture of the Gaia instrument, which is 2 telescopes. So yeah, Bepi Colombo is going to Mercury, and when it arrives in Mercury, there will be the Airbus Mercury Planetary Orbiter and a second spacecraft released, which is the Japanese magnetospheric orbiter. But the simply getting to Mercury with the electric propulsion system has been extremely difficult, with a lot of investigations and trials of the electric propulsion system and the power subsystem. But it's a sort of race against time if more power goes down. So we keep our fingers crossed for that one. And solar orbiter, yeah, the solar orbiter is orbiting the sun in an elliptical orbit, as I described. And it's going very, very close to the sun, 0.29 AU. That's 1 AU is the distance from the sun to the Earth. And they say it's delivering loads of science, solar physics. So I've kind of described spacecraft we've delivered. Now I'm going to move on to system engineering aspects. So an interface between propulsion and another department in Airbus is the orbital mechanics people calculate an orbital trajectory, and every now and then in the mission we are asked to deliver a delta V. So a delta V is a change in velocity. So it's a unit of meters per second, and we take the number of meters per second needed and put it through our favorite equation called the rocket equation. And from that, we calculate the propellant budget needed. So that's like, if you want a delta V, well, you could use 1,000 newtons for 1 second or 1 newton for 1,000 seconds. So there is a next level in the system engineering, and that is watt thrust level. So when you're going to be slowing down to enter a planetary orbit, you need to achieve all of that slowing down in a certain known amount of time. So that allows the orbital mechanics people to say how much thrust they want. And then the propulsion people, okay, well, we can give you this thrust, which is different. So do we have a brand new thruster, or just live with already off the shelf existing ones and double up on them, sort of thing, which is what we do. So thrust level and what duration is an input from the system engineers into the propulsion team. And typically the thrust level tells you what sort of technology the monopropellant sort of does up to 500 newtons, and the bipropellant does from 10 newtons up to kilonewtons. So often the thrust level tells us what sort of propellant we're going to be using. Another system level input to propulsion is the attitude control. So you might say, okay, you want high thrust for orbital maneuvers, but attitude control typically wants low thrust for delicate control. So we sometimes have to fit a number of different thruster types and even different propulsion technologies on the same satellite. And then another element to the system engineering is how many thrusters and what locations, and thrusters are burning aggressive chemicals. So there's an amount of plume contamination, it can happen. So a system level study is done into plume analysis and what the plume might be, the thruster is pointing close to sometimes. And another one which defines the whole spacecraft sort of layout is storing all the propellant. So sometimes it's, well, from a propulsion point of view, if you have two propellants, oxidizer and fuel, then you want two propellant tanks because that's cheapest and most efficient for propulsion. But sometimes the spacecraft system demands that we have 4 propellant tanks or 6 propellants, or in the case of Bepi Colombo, 5 propellant tanks. Okay, so those are all the sorts of trade-offs that we get involved in. So this is sort of orbital mechanics. So objects which are flying through space in a gravitational field, e.g. of a planet or a moon, they follow well-known shapes. So the shapes can be a circle, like a geosynchronous satellite, an ellipse. Well, the Earth orbits the Sun in an elliptical orbit. And another example of an ellipse is a launch vehicle. So you can say a launch into Earth orbit goes from the Earth and they go into an elliptical path. And so they release your satellite in an ellipse, which comes down to close to the Earth at the apogee, perigee, and far away from the Earth at the apogee. Then these are the shapes that you get when they cut a conic section. So a circle is if you cut the cone across horizontally, an ellipse is if you cut it at an angle. The parabola is when you cut it parallel to one of the sides, and a hyperbola is when you go that further a little bit more. So these are sort of highly mathematical shapes. So the extreme example of an ellipse, so an ellipse returns, but as you make that ellipse longer and longer, you get to the parabola, which is the dividing point between ellipse and hyperbola. And I list a couple of examples of hyperbolas there, which are these Oumuamua and Borisov, which are rocks that have passed through the solar system recently. Okay, so we have these prescribed trajectories, and they would just stay in that trajectory unless something else disturbs them. So there they are. We can see, for example, the ellipse of a launch vehicle in blue, and then you might take the spacecraft does a maneuver at the apogee P, and it turns into a circular orbit, which is what we do on telecommunication satellites in geosynchronous orbit. And then if at P you do more delta V, so you add more velocity, then you go into an ellipse which goes into a higher Earth orbit, say. If you add more delta V at the point P, you end up at a parabola, and even more velocity goes into a hyperbola. So now I've got some audience participation. Please, can you consider this question? So in 1971, a NASA astronaut took golf clubs and balls to the moon. So the question is, can you hit a golf ball from the surface of the moon and put it into lunar orbit? So does anybody have an opinion about that?
How do you hit it?
Yeah, you have to be able to hit it quite fast. Okay, so assuming you can give it any speed, give it any delta V, then Could you put it into Earth or lunar orbit? Any other opinions? You think you can? Yeah, you could do it. Okay.
Surely point P is on the surface, no? So it's always going to try and return the point.
Yes, absolutely right. It will be in a circle or an ellipse, and unless you hit it too hard, that's right. So you got to hit it the right amount. But you're right. That's crucial. It returns to that point. Okay. Does anybody want to develop that idea? Absolutely. Yeah. Yeah. So you can only do it if you go to the highest point of the moon and hit it horizontally. So, I mean, that's sort of, but it gives you an idea of what we're dealing with. And moving on, these are the sorts of velocities. So minimum orbital velocity on the moon, 6,000 kilometers per hour, and an escape velocity of 8,500. So when you go to the highest point on the moon, you also have to hit it give it the right velocity in that one go. And then we've got minimum orbital velocity of Earth orbit is 29,000 kilometers per hour, and the Earth's escape velocity 40,000 kilometers per hour. So we're talking 100 times the speed of cars go down the road on the moon, and 500 times the speed that your average car goes down the road. So those are the speeds we're talking about when we're dealing with satellite propulsion. So we are, the delta V's we have to deliver are in kilometers. Okay. They're huge. So they're in, like, when you go from a elliptical launch vehicle into Earth orbit, that is a delta V of 1400 meters per second, which applied on my first project. Okay. So my next bit, the propulsion engineer's favorite equation, is the rocket equation. So the analogy here is you're standing on a rowing boat, and every second you throw 10 kilograms out the boat at 100 meters per second. So the propellant, as it were, the mass you throw out, 10 kilograms, and the specific impulse is the 100 meters per second. So that is a bit like a propulsion system. You throw 10 kilograms out every second at a velocity of 100 meters per second. And you can see that the mass of the rowing boat and its contents, i.e. the propellant and you, is dropping. But with each second that passes, the additional velocity change is more than before because the vehicle is now lighter. So the rocket equation is a logarithmic equation, okay? So that delta V equals the VE, the exit velocity of the thruster, times the natural log of the mass of the spacecraft at the beginning over the mass of the spacecraft at the end. So you have mass at start, mass at end. You can work out how much propellant you need from that equation. Okay, so that's the rocket equation. And here we are. We've got, say, cold gas is simply, so typically our spacecraft are at room temperature inside. So at 20 degrees C, if you let a puff of cold gas out, it goes at 700 meters per second. Okay. Peroxide is a sort of propulsion chemical that we don't use here, although sometimes it has been used, and it's famously used in a James Bond film. When you see James Bond flying, he's using a hydrazine peroxide, not hydrazine, hydrogen peroxide system there. So the hotter the chamber temperature, the more velocity the molecules have. So 370 degrees C typical is you can use any old steel to constrain that. And then hydrazine generates a temperature. This is an indicative temperature. So the specific impulse of hydrazine is 2,200 meters per second. And moving on to NTO MMH, that's nitrogen tetroxide and monomethyl hydrazine, which is what I've used the most in most of my projects, 3,100 meters per second, and combustion chamber temperatures, which mean we have to use exotic alloys. And then hydrogen oxygen, which is like launch vehicle propellant choice, even more escape velocity, more exit velocity, and higher chamber temperatures. And then I've given you there the two types of electric propulsion, the Hall effect and the gridded ion, and they are huge velocities. So temperature is a measure of the velocity of the molecules. So when you get to the electric propulsion technologies, the very high temperatures are contained by magnetic fields. So electric thrusters are magnetic walls holding a plasma in, and the plasma is then accelerated either by magnetic effects or electric field. Okay, so those are the sort of propulsion technologies we use. And I'm moving on to my last slide now, which is an illustration of all our interplanetary spacecraft save propellant by doing gravitational assist maneuvers. So if you consider a stationary planet or moon, then the trajectory of the satellite relative to that planet or moon is symmetrical. It's the same entering and it is leaving. Okay, so the change relative to the moon is, or planet is, there is no change. But the gravitational assist maneuver achieves more velocity, so it steals a little bit of the velocity of the planet. The spacecraft gains velocity at the expense of the planet because of vector addition of the relative velocities, which I hope you can appreciate from that diagram. Okay, so yeah, the Rosetta did loads of gravitational assist maneuvers. So does Bepi, so does Solar Orbiter. They all use it to save some propellant. Okay. Yeah, that's the end of my talk. So I welcome some questions. Okay.
Thanks. Sorry, my name's Alan Ristrick. I'm retired from was Marconi originally. I've got no background in space. Are all spacecraft propulsion systems then based on the ejection of massive particles, or there are no other sorts of propulsion systems that can be based on electric effects and magnetic fields that are out in the universe?
We do have attitude control by solar pressure, so we can get attitude control from angling our solar arrays. So that is also done. Okay.
Yeah.
Um,
Can you use the Earth's magnetic field, for example?
yeah, spacecraft use magnetorquers as well. Yeah, so that's saves propellant. Yeah. Yeah, so generally propulsion is expelling mass in some way or other, but there are other ways of doing attitude control. Yeah.
More gently.
Yeah.
Thanks, Bob, for the talk as always. In terms of propulsion design, you spoke about being on telecoms before and then moving to space science. What are the differences or challenges moving from a flexible platform like Eurostar to more bespoke designs like in space science?
Well, the idea is that for the telecom satellites, you design it to start with and try and sell 50 of them. So you're down to ever cost saving measures on the telecom satellites compared to mostly trying to reuse existing hardware in a bespoke way on a science satellite. I think that summarizes it. Yeah.
Very good. Thank you.
Thanks for the talk, Bob. What's the most unusual problem that you've had in the operation of a spacecraft in your time?
Okay, well, a spacecraft being released from the launch vehicle an hour before it should have. And that is that is definitely a design feature of launch vehicles. If the launch vehicle is going wrong, it doesn't want to leave the satellite in orbit with a launch vehicle attached to it. So they just release you. So I saw that happen. So I was in a control center and we were waiting, for the mission to pass, and I turned around and my screen had turned red. Everything was alarms because it wasn't at the right time. So yeah, that was quite interesting, and that was a satellite that had to be dropped into the Pacific Ocean, complete write-off. But yeah, I suppose yeah, the recovery of the Olympus program was a great experience. So thawing out frozen solid propellant in pipes and tanks was really quite exciting.
Yes, I remember you telling me about that. And you said that you had to shut the most vital systems first to build up.
Yeah, so that was like limited power supply on Olympus. So what power was available had to go to the most important places. So the earliest telecommands which were sent were to switch things off so that what power we got was usable, because the spacecraft died in a certain configuration, so it had to be reconfigured to allow us to recharge batteries.
And perhaps ask what some of the most energy intensive systems were.
No, I can't remember.
Fair enough.
Yeah.
Thank you.
Yes, thank you, Bob. You talked about the elliptical orbit around the sun, and I was intrigued to know why you have an elliptical orbit when your conventional orbit might have given you more data. Was it because of the heat? So it got really close to the sun and then had to get away to cool down, or was it for some other reason?
So that's solar orbiter. Yeah, I think the elliptical orbit for solar orbiter was simply chosen because it allowed a gravitational assist maneuver every 200, every 500 days to do that take the
So it made it cheaper.
It's a way of doing it which doesn't need propellant. So to do a polar mission,
holes would be vastly more propellant. Yeah, and you know, it enabled it.
Cool. Thanks for the presentation. You mentioned the electric ion propulsion. That's something I've not really heard before. I was wondering what status that's at, how far developed has it been, and is it being implemented at the moment?
oh yeah,
Electric propulsion was baselined on the International Space Station. I think we launched our first EP spacecraft in about 2008, but EP electric propulsion went through a phase of popularity, followed by a phase of too many failing. So the popularity went down and then it came up, and now it's a primary choice for a lot of functions because it is 600 kilograms of xenon can do the same as 17,000 kilograms of biprop.
Thank you.
You mentioned basically the different types of propulsions. So because you've got like gases, you've got electrics, that kind of thing. How do the propulsion tanks change? What is there different sort of requirements from them as well?
Yeah. So sometimes the propellant is a gas, and therefore it's just a bottle, and you just let it out. Whereas liquid propulsion has the difficulty with liquid propulsion is we push the liquid out with helium pressurant. So you don't want the helium finding its way to the propellant outlet. And that is a real problem, okay, definitely to be avoided. So we have surface tension effect things inside the propellant tank to hold the liquid at the liquid outlet end of the tank. Okay, so we have say surface tension or simply a rubber type membrane which divides helium from propellant. Okay, so that's propellant tank sort of design in a few words.
Bob, you mentioned contamination very, very briefly, but you'll remember that on solar orbiter, it became a very, very big issue very late in the day, and it took a big Heath Robinson effort to solve the problem. And I take it the lesson was learned from that, and that future projects where contamination is going to be a problem with a biopropellant is recognised, and that's taken into account early on.
Yeah, I remember solar orbiter. Was it the bake out you were referring to? No.
No. The backflow of propellant droplets onto instruments, and we had to erect baffles all over the spacecraft to physically get in the way, which is a very, very strange way of doing it. Very late in the day, but we got away with it, but only just.
Yeah.
It's going to be there forever with those same propellants. Yeah. Because the other departments in Airbus want to fire thrusters under all sorts of conditions. So the complete combustion is not always guaranteed. And biprop thrusters by design use liquid cooling. So part of the fuel is intentionally sprayed onto the combustion chamber walls for cooling. Therefore, that liquid film is supposed to evaporate, but sometimes it won't. So droplets coming off the end of thrusters is here forever. Yes. Yeah. And we need shields. Yes.
What do you see as the future propellants?
Well, the future ones are going to be safer, cheaper, or more environmental. And in a nutshell, that's what we're working on. Okay.
Thanks for the presentation. I saw on the slides there was 2 electric propulsion methods. What's the difference between the 2 other than the velocities?
Hall effect. I think the Hall effect is a magnetic acceleration of ions, and that gives you the lower performance, but the lower performance is more reliable. Okay, so it's very good performance compared to chemical, and then the higher performance is gridded ion, which is ions accelerated by an electric field. Okay, and it does give you faster moving ions.
They're both of those.
They're both 200 millinewtons-ish, I think. But the gridded ion is more, it's just hotter, more aggressive, more erosion. Okay, more difficult to do. Yeah.
This makes me look like an idiot. What are the ions concerned about? Ions of metal? What are they?
Well,
typically to date, xenon. Xenon with 2 electrons removed.
I wondered if you ever had experience with a situation where the plumes themselves have disrupted any communications between the spacecraft and wherever it's trying to communicate to, and whether you have to consider what direction that plume's heading in and whether it's going to disrupt any communications.
Absolutely. A chemical thruster plume is also a plasma. A flame is a plasma. So plasmas interrupt electromagnetic waves. So yeah, that's part of the system engineering accommodation study to get the plumes away from the signals and things. Yes.
On LISA Pathfinder, for a long time, there was the field effect of electric propulsion, low thrusters being considered the beeps. Do you see those coming back?
No, I haven't. I'm not aware of anybody sort of managing to make them work, but maybe they are. Yeah. Feeps. Yeah, that's because the other one was colloid thrusters, wasn't it? So colloid thrusters have been flown as well. Yeah. Okay. Another electric propulsion type. Yeah. Very specialized. Feeps. The gridded ion and Hall effect are just stealing every opportunity. Yeah.
So, thank you very much, Bob, for the amazing lecture.
My pleasure.
I think we can give a round of applause. Thank you so much. I've certainly learned some interesting things about the company and the missions you worked on. I hope everyone have. I would like to grab the opportunity to advertise our upcoming lecture, which is in about a month's time, at the same location, delivered by a person who is also in the audience, my colleague Rob Hughes, about putting supercomputing power into space. And that will be on the 19th of February. So we hope you all come back and join us for that one too. So thank you very much, everyone, for coming. On the way out, can I just ask you to leave your visitor badges at the reception desk? Thank you so much.